Hey everyone. Today we're going to look at the conservation of mass energy, and while we do that, we're going to actually wrap up our final equation for the year when we do that. So before we get into what it actually is, let's start with like a sort of a simple problem that maybe looks like something you would have seen in chemistry, but we're going to keep it like really simple. I don't want to scare you away there. So for number 11, zinc can react with hydrochloric acid to form hydrogen gas and zinc chloride in a reaction that looks like this. So if you remember your chemistry at all, you know what you're looking at. If not, it's, I guess, not super important. Because let's look at the question. Let's say that 8 grams of zinc reacts with 7 grams of HCl. After the reaction, what will be the total mass of the products? Meaning, like, okay, so let's say that we took 8 grams of this zinc right here, and we mix it, or 8, come on, and we mix it or react it with 7 grams of HCl. What should we be left with? Like, how much mass should there be? Well, if we have 8 and then 7, we start with a total of 15 grams of mass. And so we have to end with 15 grams of mass. You learned that in chemistry at some point. But it turns out that if you actually did this experiment and you had like really nice fancy equipment, you would do this experiment and then you weigh all the reactants. You figure out what the mass is. And you're expecting 15 grams, because that's what you put in. But you don't actually get 15 grams. You get something a little bit smaller. Not a lot smaller. Maybe you get like 14.99999 grams. Okay, so is that 15 grams? No. Would you notice it if you did this experiment at home or like in our classroom? No, definitely not. It's such a small difference. But it's not, there is, in fact, a difference there. And in physics, we don't let that go. Mass has to be conserved. Everything's conserved in physics, right? We did momentum is conserved, energy is conserved, charge is conserved. All these things are conserved. And so in physics, we really don't like this. And again, it's not, it's a tiny amount, but we have to figure out what happened to this missing mass. Like, where did it go? And the person who comes up with the solution to this was Albert Einstein. He comes up with this idea, the conservation of mass energy. And basically what it is, and this is going to sound like very weird, is that mass can turn into energy, and energy can turn into mass. Like, basically his idea is that mass and energy, like, you think of them as two different things. Mass is like the amount of matter in an object. Like, you yourself are an object. You have mass. It's, all the things that make you up. And you also have energy, which is like a different thing. It's your ability to do work, to accomplish tasks. It's your, go get them, whatever you have energy. What Einstein says is that those aren't actually two different things. They're the same thing. They're just different versions of the same thing. Two sides of the same coin. So mass can turn into energy, energy can turn into mass, and that's where like all of our mass comes from, and where all of our energy comes from. To address this problem in question 11, where did the 0.000001 grams go? Well, it turned into energy. So this might present itself as like an exothermic reaction. There might be some heat energy released when this happens, and where did that energy come from? Well, it came from some tiny minuscule amount of mass that, again, disappeared. But in physics, nothing disappears, so where did that missing mass go? It turned into energy. So that bunch of sentences might have sounded very circular, but that's really what is actually happening here. Mass can turn into energy, energy can turn into mass. He even came up with an equation that kind of dictates how much mass turns into how much energy. And it's an equation that you've definitely seen before. E equals mc squared. So Einstein's famous equation here. If you had to guess what most of these things stand for, I think you'd get it right, but let's make sure it's all in your notes anyway. So E stands for the amount of energy that is created. And energy, just like it's been all year long, has been measured in joules. So energy in joules. M stands for mass. And again, just like all year long, the unit for mass that we use to measure things is kilograms. And see, this feels a little random to be like sticking into this energy and mass thing, but we have seen the variable, or the constant I should say, c, and it stands for the speed of light in a vacuum. 3 times 10 to the 8th meters per second. Not going to spend too much time there, because again, we talked about that the whole time we did light. Light has this speed in a vacuum, 3 times 10 to the 8th meters per second, and that's its value right in there. So, what this equation basically means is that mass can turn into energy, and energy can turn into mass. Again, these are not energy and mass are not different things. They're like different forms of the same thing, if you want to think of it like that. So let's see what we got here. So according to mass-energy equivalence, which is this idea that we're talking about, how much energy is stored in a 7-kilogram bowling ball? So you've been bowling before. A 7-kilogram bowling ball would be like probably about 15 pounds. I'm trying to think about how much that would be. So if you could turn that entire bowling ball into energy, how much energy would you have? Well, again, we have an equation that sort of tells us that. E equals mc squared. So let's plug in and see what we have. We have a 7-kilogram bowling ball, and we know that kilograms is the unit for mass. So that's what I'm going to plug in there. I'm gonna leave out my units because it's not working for me today. C, every time you see C in an equation in physics class, it stands for the speed of light in a vacuum. 3 times 10 to the 8th meters per second. And the easiest mistake to make for these problems is to leave out that square. It's important. It's part of the equation. So make sure that you have that in there. I put in one unit but not the other. It's bothering me. When you're a physics teacher, then absence of units is upsetting. So you plug these in a calculator and you get an answer of... Alright, I got 6.3 when I did this on my calculator, times 10 to the 17th. And it's energy, so we're going to measure it in joules. So again, that is 6.3 times 10 to the 17th power joules. Let's think about that number for a second. Times 10 to the 17th is a lot. It's a millions, if you want to think of it like that. Let's try and give that some context here. So if you could turn this entire bowling ball into energy, you'd get this much energy. And again, that's a ton. That is like an absurd amount of energy. That's like nuclear explosion level energy. If you could turn a whole bowling ball into energy. And what I'm trying to illustrate there is that this 15-pound object, I mean, you could pick that up. It's a bowling ball. It's heavy, but you can move it around. It's something you can work with. That bowling ball would create like more energy than you could possibly imagine. Again, it's like a nuclear explosion amount of energy. So this equation, since c is such a big number and we're squaring it, it takes relatively little amount of mass to produce a lot of energy. And in fact, that's where all of our nuclear energy comes from. We take a certain amount of mass, and in a reaction, which would be like a nuclear reaction, like the splitting of an atom or something like that, and some of that mass, not a lot, but some of it, will turn into energy. So some of that mass disappears and turns into energy. And that's where we get nuclear energy for like power plants, or where we get nuclear energy for like an explosion, like a weapon. So to try and put that into some context here, let's look at a few examples of mass-energy equivalence. So I give you like a thing, an energy in joules, and then the mass equivalent. I'm going to show the work for the first one, but then I'm just going to throw in the numbers for the rest of these. So if you take like a food calorie, like if you're reading the nutritional information on a food, and you see that it has 1 calorie, that is 4,184 joules if you were to convert it. According to this, how much mass is that converted into energy? Well, let's figure it out. We can do that using E equals mc squared. And again, I said that we're going to use 4,184 joules. So that's 4,184 joules. And to figure out how much mass that is, we're just going to solve for m. And we always know what c is. It's 3 times 10 to the 8th. And don't forget to square it. So we're going to have to divide both sides by 3 times 10 to the 8th. Well, when you do that, you get a mass of, and I have to write this down, 4.6 times 10 to the negative 14 kilograms. 4.6 times 10 to the negative 14 kilograms. So I'm going to throw that in here. Let's go with this. 10 to the negative 14 kilograms. So, oh man, how much mass is that? That's times 10 to the negative 14 is 0.0000, like 13 zeros, before you start writing a number. So when you eat like a food calorie, what you're doing is you're turning a certain amount of mass into energy, and that's where you get your energy. How much mass is it? Very, 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 very little mass. So this is like a wildly efficient way of developing energy if you can do it, because it takes just so little mass to create something. So let's talk about like nuclear power, and by that I mean like a nuclear power plant, like something that would power like a community or a city or something like that. The average American household uses, I forget what year's data I got this from, but about 10 to the 10 joules. So this is roughly the amount of energy used by an American household. If you plug this into the equation, how much mass would it take to create that? Again, this is like, it takes very little mass to create a lot of energy. So if you did this, it would take 0.0000001 kilograms of mass to power your household for a year, assuming you're in the average American household, which is 1/1,000,000th of a kilogram. You can kind of think of it as 1/1,000,000th of a pound. And just turning that much mass into energy could power your entire house for a whole year. This one, if you're not familiar with it, it sounds very strange. Fat Man, Little Boy. Those are the names of the 2 nuclear weapons that were dropped on Japan at the end of World War II. I don't know why they named them that, but they did. And how much mass turned into energy in those instances? Well, according to our equation, 0.0001 kilogram, which is 1/10,000th of a kilogram. That's it. 1/10,000th of, you can think of it like a pound, of matter was turned into energy, and that's how much, that's how powerful this sort of idea is. Indian Point Power Plant, if you know where that is, it's a little bit north of the city. It powers most of New York City, because it's a nuclear power plant on the Hudson River. How much it produces this much energy in a year, and how much mass is that? If you do the equation, about 1.1 kilograms, about 2 pounds. So in a whole year, to power most of New York City, we'll take about 2 pounds of matter, like plutonium, uranium, that type of stuff, and that's all it takes. The Tsar Bomb is famous for being the largest nuclear weapon ever detonated by the Soviet Union. It produces this much energy, and how much mass did it take? About 11.1 kilograms. About 25 pounds that would take. And the whole world, to power the whole world for a year, this is the year's figures that I used, it was 2013, that's just what I found. It would take about 11,000 kilograms. If we used entirely nuclear energy and wanted to, produce all of it using, mass that we turned into energy. So I'm trying to illustrate this idea, which is kind of interesting, that mass can turn into energy, and that it takes just so little mass to turn into a lot of energy. Now, typically, the bowling ball example, your bowling ball will not spontaneously explode into an entire nuclear bomb of energy. That would be terrifying. Everything around us would explode constantly. Rather, what happens is fractions of a neutron would turn into energy, and so that's more realistically where you would see this. But if you did that for lots and lots of neutrons, you can produce a lot of energy out of this. So, but let's get down to the type of questions I would ask you. Let's try 13 on our own, or let's do 13, 14 together. I'll have you do 15, 16 on your own, and I think that'll be good. So let's calculate the energy equivalent of 5 times 10 to the negative third kilograms. Okay, so I want to know how much energy this is equal to. If we turned, again, this much mass into energy, how much would it be? And we have an equation that describes that nicely for us. E equals mc squared. We're solving for the energy, so we're solving for E. Let's plug in the mass, which is 5 times 10 to the negative third kilograms. And then C is always, always, always 3 times 10 to the 8th meters per second. Always, always, always that value. It's a constant. Plug in carefully, and you get an answer of, I got 4.5 times 10 to the 14 joules. If you're doing this on your own and you got this wrong, especially if you got something that was like times 10 to the 6th-ish, you forgot to square C, which I think is the easiest mistake to make here. Cool. Calculate the energy equivalent of the rest mass of an electron. Okay, so again, we're energy equivalent, we're solving for E. But we need to know M, the mass of an electron, and the only reason I would expect you to know that is it's in your reference tables. It's right on the very front page. Rest mass of an electron, 9.11 times 10 to the negative 31 kilograms. So that's a really, really tiny number. Again, electrons are just times 10, unimaginably tiny. Times 3. So even when we multiply it by this really big number, I'm still not expecting a whole lot of energy out of this electron. And sure enough, you plug it in your calculator, and I'm hoping you would get an answer of got 8.199 times 10 to the 14. And it's energy, so it's measured in joules. That's not right. I'm sorry, that was times 10 to the negative 14. So that looked wrong to me. So this is times 10 to the negative 14, because it should be a very tiny amount of energy, because electrons are so tiny. Okay, pause the video at this point. Try numbers 15 and 16 on your own. I'm going to go over it in a minute anyway, but, you know, again, pause the video, give these two a shot. I think that for 15, I have you solving for the mass instead of the energy, so changing it up a little bit. But try them both on your own. I'll go over in a second. Alright, so for 15, determine the amount of matter in kilograms that must be converted into energy to yield the total energy of 1 terajoule. Okay, so we want to know the amount of matter it would take to turn into a certain amount of energy. Again, mass can turn into energy, energy can turn into mass or matter, and so how much would this take? Well, we have an equation that tells us how much. Now, that 1 terajoule is a little interesting, or a little different. Why would I expect you to know how much a terajoule is? Well, we know what a joule is. It's the unit for energy, which means that this tera part must be a prefix. And you would know what that means because you can look it up in the reference table. Looking here, a terajoule is it is 10 to the 12th joules. So, if we're plugging in for energy, we've got 1 times 10 to the 12th joules equals, this time we're solving for m, so we're going to leave that as our variable, times 3 times 10 to the 8th meters per second. And as always, please, 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 please don't forget to square that, square c. Alright, we're going to have to divide both sides by 3 times 10 to the 8th squared. And as long as you did it right, you should have gotten I got 0.00011 kilograms equals the mass. If you got something like 1,000 or something in that neighborhood, then I think you forgot to square C. So again, if that's what happened to you, I think that was the mistake that you made. So to create this much energy, and this is a lot of energy. If we look back up here, times 10 to the 12th is, again, fat man, little boy in our chart, which is a nuclear bomb. To do that, it took very, very little mass. So what if we took a 0.2 kilogram apple and turned that entirely into energy? How much would it be? Well, E equals mc squared will tell us that. So we're solving for E. We know that the mass is 0.2 kilograms. And we always know C because it's a physical constant. 3 times 10 to the 8th meters per second. And as always, we are just not going to forget to square. Okay, multiply the two, and I think you get, I got 1.8 times 10 to the 16th joules, which is an absurd amount of energy for, we're talking about like an apple here. Times 10 to the 16th, if we look at our chart up here, is, again, a nuclear power plant. It powers most of New York City for a year. this much mass, an apple turning into energy. So that's it. The important ideas here were that mass and energy are not different things, they're like two sides of the same coin. Mass, or matter, can turn into energy, and then energy can turn into matter. We can sort of switch back and forth between these two things. You don't typically see it on a large scale. Like your car will not spontaneously turn into energy, but like a fraction of a neutron might. And if you do that across enough atoms or molecules, you can create a lot of energy out of that. And this equation, E equals mc squared, tells us how much mass turns into how much energy.